Hello students. So in the previous lecture we were discussing about the osmotic pressure. So today we are going to discuss in detail about the osmotic pressure, the various kind of solutions, and we are going to start the last and the most important portion of the chapter, that is called as a Van't Hoff factor. And I hope you have gone through all the previous lectures and you are solving the daily practice problem sheet, and you are also solving the daily questions which we are discussing in the class. Okay, so let's get started. Okay, so in the previous lecture we have talked about osmotic pressure. Okay, so just doing a small recap of it. So if we consider a container, suppose we are having a container in which has two compartment which is separated by a semi-permeable membrane, right? So this was your semi-permeable membrane. So we are basically saying that suppose this side has some solution, and the other side has, say, again another solution. So suppose this was your compartment A and this was your compartment B. Now suppose this is the concentration C1, this is the concentration of this segment is C2. So we are having aqueous solution in the two compartments A and B, whose concentration are C1 and C2. They are separated by a semi-permeable membrane. So we know that semi-permeable membrane is a membrane which allows only solvent molecules to pass through it. Now depending upon the concentration, the solvent will move from one side to the other. Now if suppose we are having C1 is greater than C2, that means the solution present in the A side is more concentrated than that in the B compartment. So what I can say over here is, so if you look at this, we have already derived that pi is equals to the osmotic pressure was equal to C into R into T. So we have already told that the solvent molecules will move from the region of high concentration of solvent to a region of low concentration of solvent. So if the concentration of solution A is more than that of B, it means that the amount of solute in A side is more than that of B side. So amount of solute is more, amount of solute is less in B side. So obviously the amount of solvent in the B side would be more. The solvent in the B side is more as compared to the solvent in the A side. So during a osmosis, we say that the solvent molecule moves from the region of high concentration to a region of low concentration. We are talking about concentration in terms of solvent. We are not talking about solute. So where there is more amount of solvent will start moving from that region to the region where the solvent is less. Because C1 is more than C2, it means that solution A is more concentrated, so it has more solute particle. So the C2 side will have more of solvent particles, so this solvent will keep on moving over here. So the solvent molecules from B will just come to the side A, till both the solution have the same vapor pressure or will have the same osmotic pressure. So the solvent will keep moving from side B to A till the concentration of both the solution becomes same. Now when the concentration of both the solution will become the same, we will say that their osmotic pressure also becomes the same. So when the solvent particles from B moves to A, so what will happen? The level of the liquid will start rising in the compartment A. So if suppose if it increases to a height of h, if this liquid rises to a height of h, so we know that that height h liquid would exert a hydrostatic pressure on the solution. That would exert some pressure. So if that height column h exert a pressure, so that would stop this osmosis. So that pressure is also known as the osmotic pressure. So we have done this in the previous lecture. So we have said that pi is equals to C into R into T. So we can clearly see that osmosis is happening from, so we will say that osmosis is happening from a region of more concentration of solvent, okay, to a region of low concentration of solvent. Okay, hope this is clear to everyone. So if concentration C1 is greater than C2, so suppose if the osmotic pressure of the solution is pi 1 and the osmotic pressure of the solution is pi 2. Okay, now because C1 is greater than C2, so we can say that pi 1 is also greater than pi 2. That means osmotic pressure exerted in the solution A is more than that exerted by the solution B. So osmosis is taking from the side which has less osmotic pressure to the side which is having more osmotic pressure. So we can also say that osmosis happens from a solution of low osmotic pressure, okay, from a solution of low osmotic pressure to the solution of high osmotic pressure. Okay, hope this is clear to you. Okay, because C1 was greater than C2, it means that osmotic pressure in the container, the chamber A was more than that in B. Okay, and the osmosis we know is happening from B to A. So we'll say that osmosis is happening from, okay, the side which is having more low osmotic pressure or smaller value of osmotic pressure to the side which is having higher value of osmotic pressure. Okay, now when the solvent crosses this semi-permeable membrane and reaches to the side A, so what we will say, this solution will start diluting, okay, because the amount of solvent or the water would increase. We know that concentration is number of moles upon volume. Okay, so this is number of moles of solute upon volume. Now because more and more solvent particles are coming in this side, so the volume of the solution will increase, so the concentration will keep on decreasing. Okay, so initially C1 was greater than C2. Now after osmosis happens, the concentration of the solution A would keep on decreasing, okay, because the number of solvent particles is increasing and the concentration of this side would keep on increasing because the volume of solvent is decreasing in this side, okay, because the solvent are crossing the semi-permeable membrane. Okay, so the volume of solvent is decreasing in this side, so the concentration would increase. Now the solvent is coming to the side A, okay, so the volume of the solvent would increase, so the concentration would decrease. So one concentration is decreasing, okay, one concentration is decreasing, other is increasing. So at a certain point both the concentration will become equal. Okay, so when the concentration becomes equal, that is C1 equals to C2, then we will say that the osmotic pressure of both the solution is same, and at that point osmosis will stop. Okay, so we will say that when C1 equals to C2, osmosis will stop. Okay, now what happens exactly? It does not stop. Now what happens when C1 becomes equal to C2, the number of, because the concentrations are equal, so the number of solvent molecules passing from A to B, okay, and the number of solvent molecule passing from B to A becomes equal. So at that time there is no osmosis, there is no net flow of, okay, solvent molecule. So we'll say that osmosis is happening from a region of low osmotic pressure to a region of high osmotic pressure, or from the region of high concentration of solvent to a region of low concentration of solvent. Now if we want to write in terms of vapor pressure, okay, so if this container is suppose closed, so we know that because C1 was greater than C2, that means amount of solute over here was more. Okay, so if the amount of solute is more, we will know the vapor pressure of the solution will decrease. Okay, the concentration of this solution was less, so it means that the vapor pressure over the solution would be more. So the vapor pressure, okay, let this the vapor pressure be P1 and the vapor pressure over this solution be P2. Okay, so we know that P1 is greater than P2, okay, because this solution is dilute, so there is more number of solvent particle at the surface. Okay, so more number of solvent particle will escape and form the vapor, so more number of vapor will be formed in this side, so we will say that P1 is greater than P2. Okay, now when P1 is greater than P2, it means that osmosis is happening from a region of high vapor pressure to a region of low vapor pressure. Okay, so this will say that osmosis is happening from a region of high vapor pressure, okay, to a region of low vapor pressure. Okay, hope this is clear. So this is a very important question that can be asked in objective pattern, like 1, 2, 3, 4. All the 4 statements can be formed as a question. Okay, so hope this is clear. Now we also know the formula. Okay, so initially what we'll say that osmotic pressure, okay, in the side A was more than that in the side B. Okay, so the solution which is having lesser osmotic pressure, okay, the solution having lesser osmotic pressure is termed as hypotonic solution. Okay, is termed as hypotonic solution. Similarly, solution having higher osmotic pressure is termed as hypertonic solution. Okay, so now we are having two sides A and B. Now we know that because concentration of A side was more than that of concentration of B side, so the osmotic pressure, okay, is equal to CRT. So the osmotic pressure at the A side was more because osmotic pressure is directly proportional to the concentration. The concentration was more over here. Okay, so we'll say that this side is hypertonic because it is having more osmotic pressure, and this side is hypotonic. Okay, so we can also say that osmosis is taking place from hypotonic to hypertonic solution. Okay, so we can also say that the osmosis is happening from hypotonic, solvent is moving from hypotonic solution to hypertonic solution. Okay, hope this is clear to you. Now osmosis continues till the concentration of both the solution becomes equal. Now when the osmotic pressure of both the solution, when the concentration of both the solution becomes equal, then we'll say that both will have the same osmotic pressure. So the solutions which are having same osmotic pressures, okay, solutions having same osmotic pressure is termed as isotonic solution. Okay, so it is termed as isotonic solution. Okay, hope this is clear to you. So these are the few definition that you should know before solving numericals. Okay, so we are saying that if suppose in a container we have separated the container with a semi-permeable membrane, okay, and there are two chambers A and B. Suppose the concentration in the A side was C1 and the concentration in the B side was C2. If suppose C1 is greater than C2, okay, so we know that osmotic pressure is R CRT. R and T is constant, R is the gas constant, T is the temperature. Okay, we are carrying this experiment at the same temperature, so pi is basically proportional to the concentration. Osmotic pressure is directly proportional to the concentration. So side A is having more concentration as compared to the side B, so osmotic pressure would be more in the side A as compared to side B. So we can write that pi 1 is greater than pi 2. So the solution which is having more osmotic pressure is called as hypertonic solution, and the solution which is having less osmotic pressure is called as hypotonic solution. Okay, now we know that because the concentration is more in the A side, so the number of solute particle is more, okay, here as compared to the number of solute particles over here. Okay, so if the solute particle is more over here and solute particle is less over here, so if solute is less, then obviously the solvent would be more. Okay, here solute is more, so solvent is less, so the amount of solvent is more over here. Okay, so this solvent passes from the region of high concentration of solvent to a region of low concentration of solvent, so it will cross from B to A. Okay, so solvent molecule will keep on passing from B to A. Okay, now when the solvent is passing from B to A, so the volume of the volume of the solution is decreasing, so the concentration of this portion would keep on increasing. When the solvent molecule has reached over here, so this solution is becoming dilute. Okay, the volume of the solution is increasing, so the osmotic pressure at this side the concentration would decrease, hence osmotic pressure would decrease. So osmotic pressure decreases and this osmotic pressure increases at some concentration, both the osmotic pressure becomes equal. So when they become equal, we say that both the solutions have become isotonic. Okay, so we'll say that osmosis is happening from, okay, a region of high concentration of solvent to a region of low concentration of solvent, or from a hypotonic to a hypertonic side, okay, or having higher vapor pressure to a region having lower vapor pressure. Okay, so I hope this is clear to you. So just write it down quickly or have a snapshot of this so that you can write it in your notebook. It will give you just 1 minute to write it off. Okay, so let us just try to explain this concept, okay, through an example. Okay, suppose we have been given that, suppose we are having a container, okay, which is again divided by a semi-permeable membrane, okay, and let us say that we are having a solution A over here, okay, and let us assume that there is a solution B over here. Okay, suppose this is a solution of copper sulfate solution, okay, and let us assume that this is K4FeCN6 aqueous solution. Okay, now in the question you have been given that when copper 2 plus, okay, when copper 2 plus react with FeCN, when it reacts with K4FeCN6, okay, when it reacts with K4FeCN6, it forms Cu2FeCN6, okay, and this is a brown color PBT. Okay, so this has been given to us that when copper 2 plus react with K4FeCN6, it forms a brown color PPT. Now the question is, in which side would this PPT be formed? In which side brown PPT would be formed? A side, B side, okay? In which side would the brown precipitate be formed? Okay, so you have to just understand the concept that in osmosis only the solvent particles are moving, okay, solutes are not moving at all. So if you look at these two solutions A and B, okay, nothing has been given to us as the concentration, so we don't know anything. We just know that because both of them are aqueous solution, so just the water molecule, which is the solvent, can move from A side to B side or from B side to A side. Okay, so it would never happen that K4FeCN6 is passing into this solution or copper sulfate is passing into this solution because they are solute. Okay, so these two components will never come in contact. Okay, they will definitely be in the different region. Copper sulfate would remain in the region A, only the water molecule can go either from A to B or B to A. Similarly, K4FeCN6 would remain in this portion of the solution, in this side of the solution. Okay, K4FeCN6 cannot pass over here because it is a solute. It is not allowed to pass through a semi-permeable membrane. Semi-permeable membrane allows only water to pass through it. So copper 2 plus and K4FeCN6 would never come in contact with each other. Okay, so what would happen? There would be no brown color formation. Okay, hope this is clear to you. Again, a very basic logical question. Okay, so in this case there would be no reaction because copper sulfate won't come in contact with K4FeCN6 because two of them are separated through a semi-permeable membrane and they cannot cross the semi-permeable membrane. Okay, so only water molecules from each side can pass through this semi-permeable membrane. Okay, hope this is clear to you. Okay, so just look at this question. Now this says that what would be the osmotic pressure at 17 degrees Celsius. Okay, so temperature has been given to us as 17 degrees Celsius. We can convert it into Kelvin, so which would become 290 Kelvin. Okay, what would be the osmotic pressure of 17 degrees Celsius of an aqueous solution containing 1.75 gram of sucrose per 1 centimeter cube of solution. Okay, so we know that molar mass of sucrose is C12H22O11, so its molar mass is 342 gram per mole. Okay, mass of sucrose has been given to us. Okay, this has been given to us as 1.75. So we can calculate the number of moles of the solute. Okay, that would be 1.75 upon 342. Okay, we can calculate the molality or the concentration. Okay, so the concentration of the solution would be moles of the solute, okay, upon the volume of the solution in liters. Now 150 centimeter cube means 150 ml. Okay, 1 centimeter cube is equal to 1 ml. So this becomes 0.15. Okay, so we get the concentration of the solution. Okay, so we get the concentration of the solution. Now we can calculate. We know that osmotic pressure is equals to C into R into T. C is called as the concentration. Okay, so C is basically 1.75 upon 342 into 0.15. Okay, now the concentration is expressed in moles per liter. Okay, so R we have to express in moles, R we have to express in atmosphere liter per mole per Kelvin, which is 0.0821 or 1 by 12, whatever is given to the question in temperature in Kelvin 290. So this would be the osmotic pressure in ATM. Okay, so direct formula based question. Okay, so you can directly use the formula and calculate the osmotic pressure. Okay, hope this is clear to you. You can take a snapshot of the question and write in your notebook once the class is over. Okay, now let us read this question. This says that the osmotic pressure of blood is 7.65 atm at 37 degrees Celsius. How much glucose should be used per liter for an intravenous injection that is have the same osmotic pressure as of blood? Okay, so we know that in the question it is given that the solution has the same osmotic pressure of the blood. Okay, so we know the pressure is given to us as 7.65. Okay, so again directly formula based question. So this would be 7.65 equals to C into R into T. Okay, temperature R we can take as 1 by 12. Okay, R is basically 0.0821 liter atm per mole per Kelvin. Okay, approximately is also equal to 1 by 12. So you can also take it as 1 by 12 to minimize calculation. Temperature is given to us as 37 degrees Celsius. So we will convert it into Kelvin. So this is basically 310 Kelvin. Okay, so C into R into T. So this is basically 310. So we know that the concentration would be 7.65 into 12 divided by 310. Now the concentration is always number of moles of solute upon volume of solution. So this would be number of moles of glucose. Okay, and the volume has been given to us as per liter. Okay, that means volume is 1 liter. So this will be divided by 1. So this will be equal to 7.62 into 12 divided by 310. Okay, now we want to calculate how much glucose. So we want to calculate the mass. Number of moles we know. Okay, so glucose is basically C6H12O6. Okay, you can find the molar mass of this. The molar mass of this would be, oxygen is 16 into 6, 96. 96 plus 6 carbon, that is 72. Okay, that is 168 plus 12, that is 180. So this is 180 gram per mole. Okay, so we can write this as mass of glucose. Moles is basically mass upon molar mass upon 180. This will be equal to 7.62 into 12 divided by 310. So the mass of glucose required to exert the same osmotic pressure as that of blood would be this. Okay, so just you have to carry out the calculation, and this would be the answer in grams. Okay, you can do the calculation by your own. Hope this is clear to you. Okay, so we are just using the basic formula and most of the question in this chapter are formula dependent only. Okay, only some small portions of ionic are introduced, that we'll do in the next 2 classes when we'll complete the chapter. Okay, so just do this question now, just read it and do the question. We'll give you 1 minute for this. So this says that there is a non-electrolytic compound whose empirical formula is given to us as CH2O. Now this solution containing 3 gram per liter of the compound exerts the same as osmotic pressure as that of 0.05 molar of glucose. So we want to find the molecular formula of this compound. Okay, so just solve this now. This question says that we are having this compound. Okay, so its concentration is given as 3 gram per liter and this compound has the same osmotic pressure of that of glucose. So basically we know that both the solution have the same osmotic pressure. Okay, pi 1 equals to pi 2, we can say that. Okay, that means both the solutions are isotonic because their wave pressure are same. So pi 1 is C1 into R into T, pi 2 would be C2 into R into T. Okay, so this is basically osmotic pressure of glucose and this is the osmotic pressure of this compound whose empirical formula is CH2O. Okay, so R and T are same. Okay, data has not been given, R is always a constant, so we have to assume that temperature is also constant. So we'll say that C1 equals to C2. Okay, the two solutions will be isotonic at a particular temperature when the concentration of both the solutions are same. So we know the concentration of glucose is 0.05. So concentration of the compound CH2O should also be 0.05. Okay, so we know the concentration of this compound is number of moles of this compound divided by its molar divided by its volume. This should be equal to 0.05. Okay, now in the question you have been given that the compound containing 3 gram per liter. It means that in 1 liter of a solution we are dissolving 3 gram of CH2O. Okay, so we know the mass of CH2O as 3 grams. Okay, let the molar mass of CH2O be X. So the number of moles of CH2O would be 3 by X. Okay, so we know that number of moles would be 3 by X. Volume we know is 1 liter, it is written 3 gram per liter. Okay, this is equal to 0.05. So X we can calculate as 3 divided by 0.05. Okay, you can calculate this will come out to be 60 gram per mole. So the molar mass of this compound, okay, molar mass of this compound is 60. Okay, now let us look at this CH2O. Its empirical weight would be, okay, if we find the empirical weight, this would be equal to 12 plus 2 plus 16, that is 30 gram per mole. Okay, so the empirical weight of this CH2O is 30. Okay, and the molecular weight or the molar mass is 60. Okay, so the value of N would be molecular mass upon the empirical mass, which is 2 in this case. So if we multiply the empirical formula with 2 or with the N, we'll get the molecular formula. So the molecular formula of this would be C2H4O. Okay, so you can see that B is the correct option. Okay, so this is again a very easy level and a basic question. Hope this is clear to you. Okay, so we are saying that the two solutions will be having the same osmotic pressure or they will be isotonic when their concentration are same at a particular temperature. Okay, because these terms will get cancelled out. So the concentration has to be same. Now in the question you were given that the solution contains 3 gram. The solution is basically having a strength of 3 gram per liter. That means in 1 liter of the solution we have dissolved 3 gram of this CH2O. Okay, so let the molar mass of this be X. So we can find the molar mass from this data. Okay, concentration we know, we can find out the molar mass. We know the empirical weight of that particular molecule. So we'll get the value of N, multiply the empirical formula with N, we'll get the molecular formula. Okay, hope this is clear to you. Okay, now let us look at the concept of reverse osmosis. Now reverse osmosis is a very common phenomena that you also observe in your home. Okay, all the water purifier, if you look at your water purifier are also called as RO. Okay, so RO is basically reverse osmosis. So in a water purifier, reverse osmosis takes place. Okay, now what is reverse osmosis? It is just the opposite of the normal osmosis. So what happens in osmosis, that the solvent crosses the semi-permeable membrane from the side having more concentration of solute to the region of low concentration of solute. Okay. In reverse osmosis, what would happen? Just opposite of this would happen. That is, solvent would move from a region of less solvent concentration to a region of more solvent concentration. So that is your reverse osmosis, like opposite of the normal osmosis. Okay. So a process by which a solvent passes through a porous membrane in the direction opposite to that of natural osmosis when subjected to a hydrostatic pressure greater than osmotic pressure is called as reverse osmosis. So I will just tell you to write the definition. I will show you like the next term which is written over here, when subjected to a hydrostatic pressure greater than osmotic pressure. So I will show you with a diagram. Okay. So we say that in a osmosis, solvent always moves from a region of high solvent concentration to a region of low solvent concentration. Okay. But in a reverse osmosis, the reverse of the natural osmosis occurs, okay, when a pressure greater than osmotic pressure is subjected to that side. Okay. When the pressure greater than osmotic pressure is subjected to that side, this solvent from the low concentration of solvent, okay, solvent from the low concentration of the solvent side moves to the region of high concentration of solvent. Okay. So hope you have written this. Now let us look at the setup to understand. Okay, so this is basically the setup. So in one side we are having salt water, okay, and the other side we are having fresh water or the pure water. Okay. So there is a semi-permeable membrane in between. Okay, so this is basically a salt water. This side of the chamber contains salt water and the other side of the chamber contains the fresh water. Okay, if we look at the normal osmosis, so we know that the concentration of water would be less over here because there are solute present over here. Okay, so the concentration of water is less in this side. There is only water over there, so the concentration of water is more in that side. So the solvent molecule will keep on passing from, okay, this side to this side till the solutions become isotonic, okay, or both the solution have the same concentration. Okay. So when you exert a pressure that is greater than the osmotic pressure, okay, so when this normal osmosis was taken, so the fresh water was crossing the semi-permeable membrane and entering into the salt water side. Okay, so salt water would keep on rising. Okay, so suppose it rose to this level. Okay, from this to it rose to this level. So this column of height h would exert a hydrostatic pressure on this solution. Okay, that would stop the water molecule coming from this side to this side. Okay. So if we exert a pressure that is greater than that osmotic pressure, okay, so our osmotic pressure is basically the hydrostatic pressure that is developed over the solution, which was stopping the, okay, water to pass from one region to other. So if we exert pressure greater than that osmotic pressure, okay, so what will happen if you exert a pressure that is greater than the osmotic pressure? Okay, so the water molecule in this side would forcibly cross to this side. Okay, so the reverse of the osmosis takes place and we call it as a reverse osmosis. Okay, so just understand this. This is a very basic and a normal concept. So if initially there was a, suppose we label this as A side and this as the B side. Okay, so we know that in the A side there was a salt water, in B side there was a pure water. So the amount of water was more in the B side because A also has some solute. Okay, so the osmosis, normal osmosis would take place from the B side to the A side till the concentration of the solution becomes equal. Okay, or we'll say that till the osmotic pressure becomes equal, right? So if the solvent was passing from B to A, okay, the salt water keep on rising. Okay, after a certain time it would acquire a height h. So this column, this liquid of this column of liquid of height h would exert a hydrostatic pressure. So because of that hydrostatic pressure, B won't be able to, the solvent from B won't be able to cross the semi-permeable membrane and enter into A. Okay, so that pressure was known as, the hydrostatic pressure was known as the osmotic pressure, or the pressure that was required to stop the osmosis. Now if we apply a pressure which is greater than osmotic pressure, okay, so we are applying the pressure which is greater than osmotic pressure. Now when the solution has established a equilibrium, that is when the solvent has passed from B side to A side, we know that the osmotic pressure of both the solution would be equal. Now when we exert a pressure more than that of in the solution side, okay, when we exert a pressure in the solution side more than that of the osmotic pressure, so the molecules of water will cross from A to B. Okay, so this is the reverse osmosis. Okay, so this process is called as the reverse osmosis. So when you apply a pressure greater than osmotic pressure on the solution side, the osmosis happens in the reverse direction. Okay, that is, solvent is moving from a region of less concentration to a region of high concentration, and in the process what happens, only water is escaping out. So we have only water over here, and that is a pure water, and this pure water is used for drinking. So this is the basic phenomena that is happening in the water purifiers or the ROs. Okay, hope this is clear to you. Okay, now one more thing which you should know, when we are mixing two solutions, okay, when we are mixing two solutions and we want to find the osmotic pressure of the new solution, okay, so the osmotic pressure of the new solution would basically be pi 1 into V1 plus pi 2 into V2 upon V1 plus V2. Okay, you can also find this, okay, when you are mixing the two solution, so you need to find the new concentration, okay, and the new concentration, you know, that into RT. So even if you don't remember the formula, there is no issue, you can do it by your logic through the concept of stoichiometry. Okay, so this is the idea of reverse osmosis. When you apply a pressure greater than that of osmotic pressure, okay, so the molecules will have more pressure than the molecules which are exerting the pressure from the solvent side. So these molecules will exert more pressure as compared to these molecules. So these molecules will forcibly cross the semi-permeable membrane and enter into the pure water side. Okay, so solvent from the solution or from the side where the concentration of solvent is less is crossing the semi-permeable membrane and entering into the side which was having more concentration of solvent. Okay, so this is the concept of reverse osmosis. Okay, so now let us come into the last portion of this chapter, okay, that is the Van't Hoff factor. Now let us understand what is Van't Hoff factor and what where is the use of this concept and how this concept can be used in solving the question. Okay, so basically right now what we were talking, we were saying that colligative property is a property that depends upon the number of particles. Okay, if the number of particles is more, the colligative property observed would be more, right? So we talked about four basic colligative property. The first one was relative lowering in vapor pressure. We said that if to a solvent we are adding a non-volatile, non-electrolytic solute. Okay, we never talked about non-electrolytic, electrolytic solute, but everything before this was a non-electrolytic solute. Okay, so when you are adding a non-volatile, non-electrolytic solute to a solvent, okay, we were saying that the vapor pressure was lowering. Okay, the relative lowering in vapor pressure was directly proportional to the mole fraction of the solute. More is the number of solute added, more would be the lowering of or relative lowering of vapor pressure. Okay, the second was elevation in boiling point. Now if to a solvent we add a non-volatile, non-electrolytic solute, the vapor pressure was decreasing, so we need to heat this liquid more so that its vapor pressure becomes equal to the pressure of at the atmospheric pressure, so that it starts boiling. So we said that there is an elevation in boiling point. So the elevation in boiling point was also a colligative property because it was dependent upon the number of solute particles. Similarly, the third was depression in freezing point. Okay, depression in freezing point, again the same concept. When you added a non-volatile, non-electrolytic solute, okay, the vapor pressure over the solution decreased. Now the freezing point is the temperature where the weigh pressure of the solid and the liquid solvent becomes equal. Okay, now because the weigh pressure has lowered, so we need to increase the weigh pressure. So some amount of ice will melt at that temperature. Okay, so the solution will freeze at a lower temperature. So that was relative lowering in weigh pressure. Oh, sorry, that was depression in what I am saying. So that was basically depression in freezing point. So depression in freezing point is again right dependent upon the number of particles. So it was again a colligative property. Now if you look at the osmosis, osmosis was again, osmotic pressure was again a colligative property because it was dependent on the concentration of the solute. Now concentration means it depends upon the number of solute particles. Okay, so these were the 4 basic colligative property which we did. Okay, we considered the solute to be non-volatile and non-electrolytic. Okay, now it was observed that experiments on colligative properties of a solution reveals trustworthy results only if the following conditions are satisfied. Okay, so whenever we are doing any colligative property experiments, okay, through colligative property experiment we can find out the unknown molar mass of a compound. Okay, so again a very important fact that I can ask, suppose I want to calculate unknown, okay, we want to calculate the molar mass of a unknown compound. Okay, so if I want to calculate the molar mass of a unknown compound, okay, so what we'll do, we don't know about the compound, so we'll take a solvent, we know the weigh pressure of it, we can dissolve the this unknown compound in that and we can record the weigh pressure. Okay, so relative lowering in weigh pressure we know is equal to mole fraction of solute. Okay, so from there we know the mass of solvent, so we can calculate the moles of the solute. We also knew the amount of unknown compound that we dissolved in water, so we can calculate the molar mass. Okay, but generally vapor pressure, relative lowering of vapor pressure is not a good method to find molar mass of an unknown compound. Similarly, okay, elevation in boiling point and depression in freezing point is also not a good technique to find the molar mass of unknown compound. So what we do in lab, okay, if suppose we want to find the molar mass of any unknown compound which we formed in a reaction. So if we want to calculate the molar mass of this compound, so what we'll do is we'll dissolve this, okay, we'll dissolve this in a solvent. Okay, so we dissolve this in a solvent. Okay, now we'll record its colligative property. Okay, now we'll record its colligative property. Now which colligative property should we record? Okay, so if we want to calculate the depression in freezing point, so we have to freeze this solution. Okay, so this was at the room temperature, we took the solvent, we dissolved this unknown compound in this solvent and we decreased the temperature so that solution started to freeze so that we can calculate a depression in freezing point. But the problem was while we were decreasing the temperature, it might happen that this compound might get solidified first, okay, or it might happen that this compound might get aggregated together, they may combine together, okay, because we don't know the behavior of the compound. Okay, so we cannot lower the temperature, okay, below the room temperature because we don't know what is going to happen with this compound when we are lowering the temperature. So depression in freezing point is not a good technique to find the molar mass of this unknown compound. Second thing which we can do is we can find out we can heat this, okay, mixture and we can find the elevation in the boiling point. Okay, but again there is a problem because when we are heating the solution, again we don't know how will this unknown compound behave in this solution when we are heating it. Okay, so that also we cannot do it. Recording the osmotic pressure, again osmotic pressure, relative lowering in osmotic pressure would come out to be very small. So it is very difficult to measure that difference in the pressure. So the only thing, the only technique is left is osmotic pressure. Okay, so osmotic pressure is a very good technique to find out, okay, osmotic pressure is a very good technique to find out the molar mass of unknown compounds. So what you will do, you have the unknown compound, you take a very small amount of it, okay, a very small mass of it and dissolve it in a solvent. Okay, now we'll measure the osmotic pressure of this solution. Okay, now even a very small amount of this unknown compound would give us a considerable amount of osmotic pressure because we know that pi is equals to C into RT. Okay, so we have to multiply this with R and T. So even the concentration is low, we'll get still a good value of osmotic pressure which can be easily measured in the lab. Okay, so that is why we use osmotic pressure. Okay, so we can directly take that particular unknown compound, dissolve it in the known solvent, okay, and just measure the osmotic pressure. So we'll know the osmotic pressure, we know the gas constant, we know the temperature. So we are going to get the value of the concentration. Okay, so we know that the concentration is number of moles upon volume. Say volume of the solution was 1 liter, so number of moles would become equal to the concentration. Concentration was mass of this unknown compound, which we knew because we took some initial amount and added in the solvent. Okay, so we knew the initial mass, so we can find the molar mass. So osmotic pressure is a very good technique. Okay, this is again a very important question that is asked. Osmotic pressure is a very good technique to find the molar mass of unknown compounds. The biomolecules, okay, the molecules which are having high molar masses. Okay, so if you consider any biomolecules or polymers, okay, we know that they are having very high molar masses. Okay, so they have very high molar masses or very large value of molar masses. So concentration we know is number of moles upon volume. Okay, number of moles would be mass upon molar mass of the compound divided by volume. Now because molar mass is very high, so concentration would come out to be a very small. Okay, now because we are multiplying it with R into T, so still we will get a considerable value which we can easily record in the laboratory. Okay, so osmotic pressure can be easily recorded in the laboratory even with very small concentration of the solution. That is why we are using osmotic pressure to find the molar mass of any unknown compound or biomolecule or polymers. Okay, hope this is clear to you. Okay, so this is a very important technique. You can write it down as well. Osmotic pressure, you can write it down. Osmotic pressure is a very good technique to find out the molar mass of unknown compound. Bracket, you can write it polymers or any biomolecules. Okay, so hope you have understood that concept. Now these experiments, okay, which I have already told you, experiments to find out the molar mass of the unknown compound. So experiments on colligative property of a solution reveals trustworthy result only if the following conditions are satisfied. Okay, the first is the solution must not be too concentrated. Okay, so if the solution is too concentrated, so the number of solute particle in the solution would increase. So there can be an interaction between the solute molecules also. Okay, so that would entirely change the concept, because right now what we are assuming solution to be ideal. Okay, now if there is an interaction, then the entire theory becomes wrong. So if the solution is too concentrated, the solute molecules will start interacting and the wave pressure and the entire concept would change. So the solution should be dilute. Okay, that's why we are saying from the start dilute solution. The name of the chapter is dilute solution. Okay, Raoult's law was valid only for dilute solution. Now the second was the solute must not undergo dissociation or association in the solution. Okay, the solute which we are adding, we had assumed it to be non-electrolytic, but if the solute added was also electrolytic, so what would happen? The solute would break into ions and the number of particles in the solution would increase. Okay, now if the number of particles in the solution increased, then the colligative property would change. Okay, so we have to take care, okay, of this fact that if we are doing any experiments, okay, related to colligative property to find out the molar mass of unknown compound, the solution must not be too concentrated and the solute must not undergo association or dissociation in the solution, because if the solute undergoes association and dissociation in the solution, the number of particles would increase, and if the number of particle increases, the colligative property would change. Okay, hope this is clear to you. Now to take care of this fact that solute can undergo association and dissociation, a concept of Van't Hoff factor was introduced. So this concept of Van't Hoff factor takes care of the fact that if you are adding any ionic, okay, solute or any electrolytic solute in the solution, Okay, so this Van't Hoff factor will take care of this fact that they can either associate or dissociate. Okay, so let me just make you understand this through a example. Okay, so Van't Hoff factor is basically written as I. Okay, Van't Hoff factor is also written as I. Now, Van't Hoff factor is calculated as total number of particles present finally, okay, or the final total number of products, final total number of particles divided by initial number of particles. Okay. Now I will explain you why we are writing an expression something like this. Okay. Now suppose I added NaCl in water. Okay. What I was expecting, I added only one NaCl particle. Now when I added the NaCl particle in water, now NaCl notoriously break into two ions. So it gave two ions, that is Na plus and Cl negative, and we are adding only one particle. Okay, expecting that we are only adding one particle and measuring the different colligative properties. But NaCl notoriously it broke into two ions, Na plus and Cl negative. Okay, because it is an ionic compound. So the number of particles that we added increased in the solution. From outside we are adding only one particle, but inside the solution now there are two particles, that is cation and an anion. So the number of particles in the solvent or in the solution increases, due to which the colligative property will also change, because colligative property always depends upon the number of particles rather than the nature of particle. Okay. So if you consider the vapor pressure, okay, suppose in a container we are having glucose. Okay, glucose is a covalent molecule, so it is a non-electrolytic in nature. So when you add glucose in water, this glucose will go into the water as one unit only. It won't dissociate or associate because it is a covalent molecule. So basically you are adding just one particle. Now in the other container, suppose you are adding NaCl, one unit of NaCl or one NaCl. So one NaCl when goes in the solution becomes two particles, that is Na plus and Cl negative. So the number of solute particles is more in this side as compared to that of glucose. Okay. So if you look at the vapor pressure, because the number of solute particles is more in NaCl, okay, so the surface would have less of solvent, okay, because now it will be occupied by two particles. So the number of vapor coming outside would be less. So the vapor pressure of this solution would be less as compared to the vapor pressure of glucose solution. So we added one molecule of glucose and one molecule of NaCl, expecting that both the solutions should have same vapor pressure, because we are adding one, okay, one molecule in each of the solution. But in one solution, the particle which I added splitted into two particles and we got effectively two particles there. Okay, so the vapor pressure of the solution decreased and the vapor pressure of the solution will be more. Okay, so Van't Hoff factor takes care of the fact that if you are adding electrolytic solute, you have to incorporate the number of ions that is produced in the solution. Okay, so Van't Hoff factor is basically given as number of particles finally upon initial number of particles. So let us quickly understand, take some example to understand this. Suppose we are talking about dissociation. Dissociation means a substance is dissociating. Okay, so suppose we talk about dissociation. Okay, so let us take an example of NaCl. Okay, so NaCl would break into Na plus and Cl negative. So the final number of particle would be 2. Okay, added initially was only 1. So Van't Hoff factor of this would be 2. Similarly, if you take calcium chloride, assuming that calcium chloride is 100% ionized, so when you add this, okay, it would break into calcium 2 plus and 2Cl negative. So you added initially only one particle, but in the solution there are 3 particles. Okay, so this would be final number of particles, which was 3, divided by initial number of particles, you added only one particle. So Van't Hoff factor of this is 3. Similarly, in the solution, suppose if you added Al2SO4 whole thrice, aluminum sulfate. Okay, so aluminum sulfate, if the degree of dissociation is 100%, so this would break into 2Al, 3 plus plus sulfate ion plus 3 sulfate ion. So you added only one Al2SO4 whole thrice, but in the solution it broke into 2 Al3 plus and 3 sulfate ion. So effectively 5 ions came in the solution. Okay, so the total number of particles finally was 5, and initially you added only one particle. So Van't Hoff factor of this would be 5. Okay, so this is for the strong electrolytes. Okay, these are all strong electrolytes. We are assuming the degree of dissociation to be 1. Okay, that means they are 100% dissociated in the solution. Now let us consider a weak electrolyte. Okay, let us consider a weak electrolyte. Okay, so if we consider a weak electrolyte, say we are having a weak acid HA. Okay, so when you add a weak acid in water, now we have done this ionic equilibrium. So I have discussed the ionic equilibrium before also, before starting the 12th curriculum. So we know that the weak electrolyte would go in the aqueous solution and it would break into H plus and A negative, and there would be an equilibrium. Okay, so initially we added only one particle. Okay, initially we added only one particle HA, but it broke into H plus and A negative, and there was an equilibrium. So finally there are, like right now there are 3 particles finally present in the solution, because HA would be there, H plus would be there, A negative would be there. Because they are not completely ionized, so we cannot write the Van't Hoff factor as 3. Okay, because it has not completely dissociated. So we'll say that let the number of moles of HA be n. Okay, so let the initial number of moles of HA be n. You can assume it to be A, B, 1, 2, like anything which you want. Okay, so at time t is equals to 0, let us assume that the number of moles of HA that was added in the solution was n. So the number of particles initially was n. After say some time t, let alpha be the degree of dissociation. Okay, let alpha be the degree of dissociation. So alpha is your degree of dissociation. So we know that how much amount would dissociate. N was the initial moles, alpha is the degree of dissociation. Okay, so n alpha would dissociate. Okay, suppose you are having 10 moles. Okay, and you are saying that 50% of it is decomposed or 50% of it dissociated. So we'll say that out of 10, 50% has dissociated. That means 10 into 0.5, 5 moles has dissociated. Okay, so the number of moles remaining would be 10 minus, okay, 10 into 0.5. So we'll write this as, if the initial mole was n, alpha is the degree of dissociation. So n alpha would be the amount of A dissociated. So amount of A left would be n minus n alpha. Okay, now 1 mole of this was giving 1 mole of H plus, 1 mole of HA was giving 1 mole of A negative. So n alpha which reacted, okay, would give n alpha of H plus. 1 mole of HA which reacted gave 1 mole of A negative. So n alpha which reacted would give n alpha of A negative. Okay, so if you calculate the total number of particles finally, okay, so this is the total number of particles finally. Okay, now in the final solution there are 3 particles available. Okay, that is HA, H plus and A negative. So the moles of HA was n minus n alpha, of that of H plus is n alpha, and that of A negative is n alpha. Okay, so when you add this, you can clearly see that they will cancel out. So we are left with n plus n alpha. I can write this as n taking as common into 1 plus alpha. Okay, so Van't Hoff factor of this would be total number of particles. Okay, total number of particles finally, which was n into 1 plus alpha divided by total number of particles initially. Initially we took it as n, okay, n number of particles of HA. So I in this case would be 1 plus alpha. Okay, so I in this case is 1 plus alpha. Okay, so I in this case is 1 plus alpha. So you can clearly see that alpha will always be, like the value of alpha is generally between 0 to 1. Okay, so for dissociation, okay, I will always be greater than 1. Okay, so for any dissociation, of the particles I will always be greater than 1. Okay, so you can write this quickly now. So this is how you do it for a strong electrolyte, and this is how you do it for a weak electrolyte. So Van't Hoff factor is basically the total number of particles finally upon the initial number of particles. Okay. Now let us take another example. Okay. Let us say that we are saying that we are having calcium chloride and its alpha is 0.7. Find its Van't Hoff factor. Okay, or suppose we are having Al2SO4 whole thrice. Okay, alpha is given as 0.5. Find its Van't Hoff factor. Or suppose we are having a weak acid, say acetic acid. Okay, alpha of this is 0.25. Okay, find the Van't Hoff factor. Okay. So what we'll do, because now everything in every case is alpha was given, that means all of them are weak electrolyte. So we'll do it the same way. Okay, so calcium chloride is dissociating into, so calcium chloride is basically dissociating into, so calcium chloride is dissociating into calcium 2 plus 2Cl negative. Okay. Let the number of particles, initially we don't know, let it be n. Okay. Now because alpha has dissociated, alpha amount has dissociated, so after time t, we'll say that we are left with n minus n alpha. Okay. 1 mole of this is forming 1 mole of this. Okay. So n alpha would form n alpha. Now 1 mole of calcium chloride is forming 2 moles of chloride ion. So n alpha which reacted would form 2n alpha. Okay, so we'll say that the total number of particles finally, okay, the summation of all the particles finally, okay, would be n minus n alpha plus n alpha plus 2n alpha. Okay, so this will get cancelled out, so we'll get n 1 plus 2 alpha. Okay, now Van't Hoff factor is, would be total number of particles finally, okay, which was n into 1 plus 2 alpha divided by total number of particles initially, which was n. So we'll get the value of I as 1 plus 2 alpha. Now alpha value is given to us as 0.7. Okay, so this would become 1 plus 2 into 0.7, which is 2.4. Okay, so Van't Hoff factor of this would be 2.4. Similarly, we can calculate for Al2SO4 whole thrice. Okay, so Al2SO4 whole thrice is, now why I am like making you do these basic level questions, they are very basic or easy questions, but they are very useful while solving a question. Okay, especially on the Van't Hoff factor. So you should be having a very clear cut idea how to like find the Van't Hoff factor, because if you calculate the Van't Hoff factor wrong, the question will become incorrect. Okay, so this would break into 2Al3 plus and 3 sulfate ion. So at time t is equals to 0, let us say that this was having n, okay, as the number of moles. Alpha is the degree of dissociation, so n alpha would dissociate, we will get n minus n alpha. 1 mole of this is forming 2 moles of Al3 plus, so n alpha which was decomposing would form 2n alpha. 1 mole of Al2SO4 whole thrice was forming 3 sulfate ion, 3 moles of sulfate ion, so n alpha which would decompose would give us 3n alpha. So total number of particles finally would be n minus n alpha plus 2n alpha plus 3n alpha. Okay, so this is clearly 5n alpha, so you can write this as n plus 4n alpha. So this would be n 1 plus 4 alpha, n into 1 plus 4 alpha. So Van't Hoff factor would be total number of particles finally divided by initially, so initially was n, so when you divide with n, n gets cancelled out, so I comes out to be 1 plus 4 alpha. Now alpha was 0.5, so Van't Hoff factor would become 3 in this case. Okay, similarly you can find out for acetic acid. Now acetic acid is a weak monoprotic acid. Okay, so the acetic acid would decompose and it would give acetate ion plus H plus. Okay, now if the initial mole was n, so suppose alpha is dissociating, so we'll get this as n minus n alpha. 1 mole of this is forming 1 mole of acetate ion, so n alpha would form n alpha of acetate ion. 1 mole of acetic acid is forming 1 mole of H plus. So N alpha amount would form N alpha of H plus. Okay. So the total number of particles finally would be N minus N alpha plus N alpha plus N alpha. So this would be N, we are taking it as common, 1 plus alpha. Okay. So Van't Hoff factor would be total number of particles finally divided by initially. Initially we are taking it as, assume it to be N. So alpha I will get as 1 plus alpha. We'll put the value of alpha, we'll get the value of I as 1.25. Okay. So you need to be very clear, okay, what to do and how to do. Okay. The calculation of Van't Hoff factor should always be correct. You should never mess it up. This is a very easy concept. This is a very basic concept. Okay. So you have to understand, whenever alpha is given to you, it means that it is assumed to be a weak electrolyte. If alpha was not given to us, okay, so we'll assume the alpha to be 1, we'll assume it to be a strong electrolyte. Okay. Then we can say that alpha would be 3, because this would get 3 number of particles. This would give 5 number of particles. Acetic acid can never be a strong acid. Okay. Only in infinite dilution it can act as a strong acid, but in general we will consider it as a weak electrolyte and we will say it is the Van't Hoff factor is 1 plus alpha. Okay. So this is how you calculate the Van't Hoff factor for different, okay, substances. Now let me just take one more example. So if I write for a general dissociation reaction, suppose we have been given that 1 mole of a substance is, okay, dissociating into n moles. Okay, 1 mole of a substance AN is dissociating into n moles. Okay, so find out the Van't Hoff factor. Okay, I, if alpha is the degree of dissociation. So we'll say that at time t is equals to 0, let the number of moles be A. Okay, I am not taking it as N because N is already there in the compound. So we'll get confused. So we will take another quantity which is A. Okay, so after time t, we know that alpha is the degree of dissociation. This is the equilibrium. Okay, so we'll say that the amount of AN dissociated is A alpha. So the leftover would be A minus A alpha. 1 mole of A is giving, 1 mole of AN is giving n moles of A. So A alpha would give N into A alpha. Okay, so the total number of particles finally would be A minus A alpha plus N A alpha. Okay, so this would be A. Okay, so I can write this as minus, or we can take alpha as common. Okay, we can take A alpha as common. Okay, so we can write this as N minus 1. Okay, so total number of particles would be A plus A alpha into N minus 1. So Van't Hoff factor of this would be A 1 plus alpha into N minus 1. Okay, just taking A common now. So we'll cancel out the initial number of particles which was A. So the Van't Hoff factor of this would be 1 plus alpha into N minus 1. Okay, hope this is clear to you. Okay, if alpha is 1, okay, if alpha is 1, that means this is 100% dissociating. So if alpha is 1, you will have to put this value as 1. So this will become 1 plus N minus 1. Okay, so eventually we will get the value of I as N, because if it is 100% dissociated, that means this would completely go away from the solution and n number of particles would be formed. So Van't Hoff factor would be n in that case. Okay, so this is for a case of dissociation. Now let us look for association. So we are saying that for dissociation, Van't Hoff factor will always be greater than 1. So this is 1 plus something. Okay, if it is, okay, 1 alpha is 1, then I was equal to n. So for dissociation, Van't Hoff factor is always greater than 1. Now let us consider an example of association. Now what do you mean by association? Okay, association is basically the molecules would associate together. Okay, or when we take molecule, it goes in the solution and they associate with each other. Okay, so the common example of this is acetic acid. Okay, the common example of this is acetic acid. When we take acetic acid in a non-polar solution, okay, the acetic acid dimerizes into this. Okay, you might have studied this in chemical bonding. So when you are taking acetic acid, 2 moles of acetic acid dimerizes together. Okay, dimerize mean the 2 molecules are getting associated. Trimerize mean 3 molecules are getting associated. So this dimerization happens because of hydrogen bonding. Okay, so this dimerization happens due to hydrogen bonding. So if you take acetic acid, okay, the another acetic acid can form, okay, a hydrogen bond, okay, and the molecule can get dimerized. Okay, so we'll say that whenever we are taking acetic acid, okay, so acetic acid will generally dimerize. Now this dimerization takes place only in non-polar solvents. Okay, in non-polar solvents acetic acid dimerizes, because in polar solvent it will behave as a acid. Okay, so in non-polar solvent it will not behave as an acid, so the 2 molecules will come together, form hydrogen bond and form a dimer. Okay, so if it is forming a dimer, so this would be the reaction. Okay, so let us say that we are taking a case of dimerization. Okay, so what we are saying, in a dimer 2 molecules would come together and dimerize. Okay, if the degree of dimerization is 100% or the degree of association is 100%. So what we'll say, we added 2 particles initially, okay, and in the solution it became only 1 particle. So the final number of particle was 1, okay, and the initial number of particle was 2. So Van't Hoff factor would be half. Okay, now if it forms a equilibrium, okay, if the dimer form A2 is the dimer form, forms the equilibrium, then let us assume that at time t is equals to 0, the number of moles of A that we added was n. After time t, alpha was the degree of association now. Here alpha was the degree of dissociation, we are assuming that alpha is the degree of association. So initial moles was n, alpha is the degree of association, so the number of moles associated would be n into alpha. Okay, so that is independent of stoichiometry. If n is the initial number of moles, alpha is the degree of association, n alpha would, okay, form the dimer or would associate. So n alpha would dimerize or would associate. Now we know that 2 moles of A is forming 1 mole of A2. 2 moles of A is forming 1 mole of A2. So 1 mole of A would form half mole of O2. Okay, so the n alpha that is reacting would form n alpha by 2 moles of A2. Basic stoichiometry we are doing. Okay, so we'll say that total number of particles finally is n minus n alpha plus n alpha by 2. Okay, so let us just take n as common, so we can write this as 1 minus alpha plus alpha by 2. Okay, so we can write this as n into 1 minus alpha by 2. Okay, so Van't Hoff factor we know is the total number of particles finally, okay, which is n into 1 minus alpha by 2 divided by total number of initial particle. Initial was n, okay, so we'll write I as 1 minus alpha by 2. Okay, so we'll write I as 1 minus alpha by 2. Now we can see that alpha will have some value because we are subtracting it from 1. So Van't Hoff factor for any association reaction is always less than 1. Now if alpha was 1, that means 100% dimerization was happening. Okay, if alpha is 1, that means 100% dimerization is happening. So if you put the value of alpha as 1, you will get I as half. Okay, so Van't Hoff factor will always be less than 1 for a association reaction. Okay, hope this is clear to you. Now if we are considering trimerization, okay, if anything is forming a trimer, trimer means 3 molecules of a compound would associate together to form a trimer. Now if the degree of trimerization or the degree of association is 100%, so we'll know that we are adding 3 particles of A and it is converting into one particle eventually. So we have added 3 particles in the solution, but because the extent of trimerization was 100%, so it converted eventually into 1 particle. So Van't Hoff factor in this case would be number of particles finally was 1 upon initial was 3. So I would be 1 by 3. Okay. Now if it forms an equilibrium reaction, then let us assume that initial number of particles was n. After say some time t, alpha amount dissociated, so this would be n minus n alpha. Okay, so 1 mole of this was giving 3 moles of A was giving 1 moles of A3. Okay, so 1 mole of A would give 1 by 3 moles of A3. So n alpha which reacted would give n alpha by 3. So I can write the total number of particles finally as n minus n alpha plus n alpha by 3. Okay, we can take alpha n as common. So this basically 1 minus alpha plus alpha by 3. So this would be 1 minus 2 alpha by 3. Okay, so Van't Hoff factor would be this is the final particle divided by initial particle. So this would be 1 minus 2 alpha by 3. Okay, hope this is clear to you. If alpha is 1, that means 100%. So it will come out to be 1 by 3. So this is also correct. So if a general reaction we can write, if we have been given that n moles of a compound, okay, associates to give 1 mole of a compound, that means n moles of A, okay, are associating together and giving An. Okay, the opposite was dissociation. An was dissociating into n moles of A. So 1 mole of An was dissociating into n moles of A in the backward reaction. In the forward reaction, we will say that n moles of A is associating and giving us 1 mole of An. Okay, so suppose this is the equilibrium. So the reaction has attained equilibrium. So at time t is equals to 0, let us assume the number of moles to be A. Okay, we are not taking it as n because there is already a n over here. After say some time t, alpha amount of this associated. So we know that A alpha amount would associate. So we'll be left with A minus A alpha. Now n moles of this is giving 1 mole of An. So 1 mole of A would give 1 by n moles of An. Okay, so A alpha that reacted would give us A alpha by n moles of An. So the total number of particles finally in this case would be A minus A alpha plus A alpha by n. Okay, so we can take A common over here. So this is 1 minus alpha plus alpha by n. Okay, this is the total number of particles finally. So Van't Hoff factor would be total number of particles finally divided by initial particle. So initial particle was number of particle was A, so they will get cancelled out. So we'll get this as the expression. Okay, hope this is clear to you. Okay, hope you are writing it also. Okay, now just let me do one thing. We'll just complete the class today. So now let us consider any coordination compounds. Okay, so a coordination compound, now we'll just tell you the basic how do you decompose a coordination compound. We'll do it in detail when we are doing coordination chemistry. So suppose we are having a salt something like K4FeCN6. Okay, suppose we are having salt something like K4FeCN6. Okay, so whenever you are taking any coordination compound in the aqueous solution, so just remember you have to take out the complex part. Now what is the complex part? The one which is written in the square bracket. So they will come as it is in the solution. So the one that is written in the square bracket will come as it is in the aqueous solution. So this would break as 4K plus, and this is the complex part, okay, that is written in the square bracket. So that would come as it is. So this is FeCN6 4 negative. Okay, so the Van't Hoff factor of this, if the degree of dissociation is 100%, would be 5. Okay, we added 1 particle, but we got 5 number of particles in the solution. Okay, and this was the 100% dissociation. So this is not present now, only 5 ions are present. Okay, so if we are taking say K3FeCN6, okay, so if we are taking K3FeCN6, okay, so this would dissociate, the square bracket or the complex part would come as it is in the aqueous solution, and the cation outside the cation or anion outside the square bracket would ionize. So this would give us 3K plus, and this component would come as it is. So this is FeCN6, 3 negative. So clearly if the degree of dissociation is 100%, so it is giving 4 ions, so Van't Hoff factor would be 4. If it is alpha, then you can calculate, this is N, okay, N minus N alpha, this would become 3 N alpha, this would become N alpha. You can find the total number of particles finally, you know the initial, you can divide and you will get it. Similarly, if you are having say Cr H2O6 Cl3, okay, or say Cl2. So in this case you can see that this is the complex part is now the cation, okay, and outside the complex part there are 2 Cl, okay, they will ionize in the solution, the complex will come as it is and they do not, okay, the component inside the square bracket does not ionize. So this will come as Cr H2O 6 3 plus 2 plus plus 2Cl negative. We are just balancing the charge, 2Cl goes out as 2Cl negative, so this complex will have 2 positive charge. Okay, so the Van't Hoff factor of this would be 3 in this case. Okay, hope this is clear to you. Okay, so just quickly, all the formulas of the colligative property now should include this Van't Hoff factor. Okay, because if the particle, if the solute add is electrolytic, so we have to include the total number of ions, okay, because the number of ions was increasing, so the colligative property would change. So we have to incorporate this Van't Hoff factor. Okay, so the relative lowering wave pressure formula would become P naught minus P upon P naught equal to I into mole fraction of solute, Van't Hoff factor into mole fraction of solute. I will come to this tomorrow because there are some question in the DPP based on this formula, so you can just solve it using the formula. Similarly, the elevation in boiling point was delta TB equals to Kb into m. Now if the solute is electrolytic, okay, so you have to take the number of ion as well, so the formula becomes I Kb into m. Similarly, delta Tf becomes I Kf into m. Osmotic pressure becomes I into C into RT. Okay, so just you have to calculate the value of I and you will get the different colligative properties. Okay, so hope this is clear to you. Okay, so today in today's lecture we have discussed about Van't Hoff factor. Just I have introduced you the formula. In the tomorrow's lecture I will just like make you solve some questions on this. Okay, and I will also show you how this expression is coming, and also we'll do some good level problem solving. So tomorrow's lecture and the Monday's lecture will basically be the solving on solutions. Tomorrow will be a basic JEE mains plus little bit of advanced level question solving. Monday would be a very tough level, Olympiad level problem solving. Okay, so I hope you have understood the concept of Van't Hoff factor. Just go through the lecture once, just calculate the Van't Hoff factor by your own, the different molecules which you have done today. Okay, so this is it for today. Tomorrow we'll catch for some more interesting session and we'll be discussing more about Van't Hoff factor and we'll do lot of problem solving. So tomorrow's lecture would be very important because we are going to see the different kind of questions that are formed from this topic. So this is it for today.